Hello, I would like to warmly welcome you to our webinar focused on our topic AFM in SEM. My name is Veronika Hegrova and I'm the application engineer. Today I'd like to talk about the in-situ analysis of mechanical, electrical and magnetic properties. As we are broadcasting, there are approximately 30 seconds of delay. And so you are muted. Anyway, I would like to encourage you to ask questions in the chat window. My colleagues will answer them loud, and at the end, we'll choose a few of them to answer them loud. So first, let me introduce NenoVision company. NenoVision was founded in 2015 as a spin-off of Brno University of Technology and Central European Institute of Technology, which is located here in Brno. Brno is a city in the Czech Republic, and it's home to exceptional universities and research institutions. It is the leading center of scientific instrumentation development. Approximately 30% of all scanning electron microscopes come from here. And so there is quite long history related to electron microscopy. From industry, there are Thermo Fisher Scientific Division of Electron Microscopy located here, and Tescan Orsay Holding was founded here as well. Similarly, with institutions and universities, there is Brno University of Technology and, for instance, Institute of Scientific Instruments. So there is no surprise that NenoVision was founded here. We developed Lite Scope. It's a unique atomic force microscope, which can be integrated to scanning electron microscopes. So in this webinar, I'd like to briefly talk about AFM in SEM, Lite Scope and its benefits, and then focus on various measurement techniques, showing them on a few application examples. So let's start with motivation, why we want to combine AFM and SEM technology. Atomic force microscopes and scanning electron microscopes are two of the most used and, in fact, complementary techniques for the sample analysis in the nanoscale. Nevertheless, since the principles which how they are observed and interact with the sample surface are completely different, they provide very different set of information. AFM monitors interaction between a physical probe and the sample surface. It has very high resolution, up to tens of nanometers. Scanning electron microscope observes and analyzes the surface using focused beam of electrons. So it has very good resolution in lateral dimensions, up to 0.5 nanometers. Let's have a closer look at the benefits of AFM and SEM solution. As we are integrating AFM inside SEM, in-situ analysis is possible, and we can measure multiple modes together and obtain complex information about the sample surface. And we can use SEM for easy localization to the region of interest and navigation. So I'd like to tell something more about these three benefits. In-situ correlative analysis means that all measurements are done at the same time, in the same place, and under the same conditions. So there is no need of sample transferring between the devices and contamination, possible contamination during analysis. Our scientific ambassador is Mark Willinger from ETH Zurich, who nicely said that LiteScope is like a Swiss Army knife inside your SEM. So it means that basically you add AFM modes to the SEM capabilities. So you actually get more. And with this AFM in SEM solution, we have unique method of multidimensional correlative imaging, which enables simultaneous acquisition of AFM and SEM data with seamless correlation into 3D images. So if we measure the topography and visualize it here, we can measure hardness together with material contrast from SEM and, for instance, composition from EDS. And the third one is the fast and precise navigation. As we measure in SEM, it's extremely easy and precise to localize and navigate the probe to the area of interest. So there are some experiments that usually are impossible without these two devices together. And also you can use SEM to control the probe even during the analysis. And so let's move to the LiteScope itself. LiteScope is composed of, or LiteScope head is composed of the scanner, on which is the sample in usual SEM stub. There is a probe inside of probe holder carrier, and there are macromotors. So you can use stage for moving under the objective, and then scanner and probe can be moved separately. So some of the LiteScope specification, I don't want to talk about everything, but LiteScope is quite small. It has less than 12 millimeter or 12 centimeters to 8 centimeters. The height is approximately 36 millimeters, and it weighs less than half of the kilogram. We can measure in usual vacuum ranges as the SEM provides, and the scanner configuration can be either in open loop or closed loop. And so how does the setup look like? So we have the SEM chamber. LiteScope is fixed onto the stage. Via feed-throughs, it's connected to the controller nanobox, which is connected to the computer, which is used for operating SEM. So you don't need any other computer for that. This way you can measure AFM and SEM simultaneously. But how? I have a scheme here showing the probe and the electron beam. They are close to each other, and we have electron beam focused to one point. And so we are scanning moving with the sample, analyzing simultaneously both of these signals. So we get the SEM, we get the AFM topography image. At the same time, we post-process that we get rid of the offset, and we have the three-dimensional image. LiteScope enables multimodal characterization. We divide the techniques into 4 groups, and I will be talking about most of them today. So mechanical properties are the first one. The electrical properties providing the conductivity map or the surface, measuring the surface potential. Piezoelectric domain imaging, and magnetic properties measured by magnetic domain imaging. For measuring the different properties, we need different probes and probe holders. We are using self-sensing probes. There are several types of them. One of them are tuning fork based it's called Akiyama sensor. which uses tuning fork to oscillate with the cantilever, and it is for AFM and energy dissipation, or for magnetic measurements with a tiny magnetic tip. There are piezoresistive based probes, nanoprobe electric, for several different measurements and modes, or piezoresistive self-sensing and actuating probes for force distance spectroscopy. And there are also other tips which can be used. For instance, for nanoindentation is Berkovich tip. So let's have a closer look at mechanical, electric, and magnetic properties. These techniques are useful in several application areas, such as in material sciences, nanostructures, semiconductors, and life sciences. And let's have a look at each of these properties separately. Mechanical properties are intensively studied in material sciences, such as measuring the dimensions of low-dimensional materials or nanostructures, or the roughness measurement is important for knowing the influence of roughness on, for instance, the device performance, so how it is linked. Then features which are important to link together are also elastic properties. And they are generally studied, for instance, for automotive industry or life sciences to know what the cell or the protein does when the force is applied. These properties can be measured by atomic force topography, elastic properties by energy dissipation for the mapping. We see the topography image in the upper part, and energy dissipation in the lower part of polymer blend, polystyrene, and the polyethylene. So we see that softer is polyethylene than the polystyrene of this case. Another techniques used for measuring elastic properties are force distance spectroscopy or nanoindentation, where we apply the force and get the graph from which we find Young modulus, the hardness, toughness, etc. So surface height and depth measurements are one of the most basic measurements of or analysis of in material research, together with material composition. It helps to determine the precise dimensions of 2D materials or 1D materials, or to control the fabrication processes and the material quality. For roughness analysis, also for photovoltaics or solar cells, it's important to know the roughness because the device is acting differently. And for instance, in pharmaceutics, it's important to know the sizes of pores and how the treatment stays in the pore. So that's the roughness analysis for. We use stepping mode frequency modulated AFM, and we use Akiyama tuning fork probe to measure in the tapping mode to minimize the risk of sample and tip damage. And so we oscillate with the cantilever at its resonance with constant amplitude. But due to the topography changes, the resonance frequency changes as well. It shifts, and so if there are feedback off, so the probe will go horizontally all the time, then there are some changes. And so if we use the feedback and track the frequency changes and keep the cantilever oscillating at resonance frequency, the probe needs to move, and so this movement is actually the topography of the sample. I have an example of high-resolution measurement. It's a silicon carbide sample. It's AFM calibration standard. And so this sample has nominal step height of less than a nanometer, and we were able to measure this Z step. And so we are in the limit. So we measured the step height of these terraces. Another example is a sample of coccoliths. They are calcium carbonate structures with very tiny features on its surface. We see the AFM topography image and the error, and we see in the detail and in the height profile that we are able to recognize 20 nanometer structures in lateral dimensions and the nanometer structures in Z-axis. And so energy dissipation maps the local elastic properties, obtaining the qualitative analysis or qualitative information about the sample surface. The elasticity of the tip sample collisions are linked to the energy dissipation, and the amount of energy dissipated from the sample is linked to the excitation voltage, which the feedback uses to maintain the same amplitude of oscillations. So then the harder part of the image is darker because it has a smaller drive signal used to maintain the same frequency, same amplitude, and in the opposite way, softer is brighter with higher amplitude of the driving signal. So we see again the polymer blend of the brighter, softer part and darker, harder part. Another technique for analysis of local elastic properties is force distance spectroscopy. The toughness or the sample adhesion can be measured from these curves. The area is firstly localized and navigated the tip to this area. Then we use the force to push to the sample while choosing the depth. And then we go away from the sample. So we see the load and unload showing the, so we are able to know the toughness from the slope of the curve and the adhesion. So there are different information which we can get from the spectroscopy. I have an example from life sciences. We were measuring the protein nanowires, which have quite unique mechanical properties, and they are studied to be used in the biomedical applications. They are fabricated from a solution and released to the filter. So now we see the released nanowire or protein, and we see that we localized the protein, and we were able to determine the dimensions of the protein. And another part of the experiment was to find the mechanical properties of the nanowires hanging between the pillars. So we see the probe, we see the quite big pillars comparing to the nanowires, and we see the nanowires. So we used the force distance spectroscopy to find the elastic Young modulus and the strength between breaking of the nanowire. And you can see during the measurement that we were tilted in SEM, we were able to see the tip and push the nanowire to deform either elastically or plastically. So here is the breakage as the wire fractured. So with Lite Scope in SEM, we were able to precisely target the protein, and we were able to see what's going on during the measurement, during the deformation. Another technique for measuring the mechanical properties is nanoindentation. Is additional module on Lite Scope. It enables us 3-in-1 study of composition, the topography, and mechanical properties. We see that we have the Lite Scope in a different configuration, and there is the nanoindentation head. We use Berkovich diamond tip to measure the force distance curves, and there is optimal procedure how to measure. So as we have AFM, Nanoindenter, and SEM together, we are able to optimize the depth of the indent, because we can first measure the roughness of the sample. Then we go with the nanoindenter to the area of interest and measure the Young modulus and hardness. And then we can go back with the AFM probe to measure the topography after the indentation. So I have an example of high-speed steel. We can see the SEM, the nano indents. The indents were made using the same force, but as there are different hardnesses of phases, there are different sizes of indents. So we measured the topography for roughness and later for the indent. We could see that there is some pile-up effect as we when pushed inside the material, and we could measure the height profile. So we got the Young modulus hardness and the topography, what's going on. Let's move to the electrical properties, which are quite interesting to link not only to the topography, but also to the material characteristic, as well to understand the material deeper. Electrical properties are extensively studied in batteries and alloys, or in the semiconducting devices such as integrated circuits or chips, or in the photovoltaics to improve the electronic performance or to find the failures. The conductivity map can be obtained using conductive atomic force microscopy mode. We see half of the image as the topography, the other half is conductivity. And so we see the microcrystalline silicon grain sample, and there are visible grains which are conductive comparing to the rest of the sample. Another electrical property is the surface potential, which we can measure using Kelvin probe force microscopy. Here is a reference sample of aluminum, silicon, and gold interface. And so we can see the different surface potentials because they are different materials. So conductive AFM analysis of the sample surface is measured using topography in the contact mode. And at the same time, we are measuring current through the sample in each point of the map. So there are variability in the experimental designs. In our case, we apply bias voltage to the tip, and simply we measure where the sample is more or less conductive. I chose an example from semiconductors. Failure analysis and defect analysis is very important in order to know the performance of the device and where are the leakages, etc. And the optimization of sample preparation and analysis is important. So the easiest way is to find the area of interest in SEM, etch the sample, and do the analysis all under in-situ conditions. So I have an example of bipolar junction transistor in cross-section. We see that there are doped layers under the transistor, and these can be used for switching or amplification of integrated circuits. And so if we measure SEM and the AFM topography together and combine it with the conductive AFM, we see that there are different layers, more or less conductive, and not always it's connected to the topography. So we were able to see the contrast in SEM and to see the sample complexly and see that the current is independent of SEM material contrast in some points. Measuring the surface potential is a bit more complicated, so I have a bit longer description here. There are three possibilities in the setup what can happen. So we have the sample and tip, which are not in the contact, so they have different work functions and different Fermi levels. Now, when they get into the contact, the Fermi levels equalize, but shift the vacuum levels, and so there is a contact potential difference which emerges between the tip and the sample. And so what we want to do, we want to minimize this contact potential difference by adding some voltage, equalizing the vacuum levels. So that's exactly how we measure the Kelvin probe force microscopy. In the first pass, we measure the topography. And then in the second pass, we follow the topography and minimize the contact potential difference in each point of the map by adding the DC voltage. And this DC voltage is actually the KPFM signal. So we see that brighter is a higher potential, darker is the lower potential area. I have an example from steels and metal alloys. Here, multimodal analysis is quite interesting and is useful in robotics or automotive industry. So if we are able to connect these information together, we can understand the material better. So I have an example of calcium-rich precipitation of an alloy. It's perspective biodegradable material with potential use in prosthetics. And so we studied the precipitation hardening. For that, we needed to know the shape and size of the precipitate and composition of the precipitate. So we chosen one precipitate. There was quite uneven surface, so only some of the islands were actually precipitates, even though it looked quite similar. And so the Kelvin KPFM signal helped us to recognize them because they have quite different potential than the rest of the sample. And so we were able to easily localize the islands and navigate the area of interest in SEM without damaging the probe because there were quite big particles there as well, and then use KPFM to identify the precipitate. Another example is from semiconductors field from defect analysis. So we have a CMOS type chip in a cross section, and for defect analysis, it was important to know which plug is brighter in KPFM, which one is darker, if the pins are alternating between two values or not. So we could use all three in one study to know the topography, the SEM, and the KPFM. Let's move to the measurement of magnetic properties. Analysis of local magnetic property domains are used in material sciences to determine the changes in crystallization domains of nanostructures or in electronics and spintronics. There is used magnetic force microscopy technique. And so we see the topography and magnetic signal here of the hard disk. So how we measure? We measure MFM in two-pass technique. In the first pass, we measure the topography. In the second pass, the probe is repeating the topography trajectory and measures the phase shift of the probe oscillations, which is now the MFM signal. And so if we have a look at the scheme, there are same oriented domains as the tip, so they are dark. And we have the counter orientation, which are bright. And the rest is something between. And so an example is from steels and metal alloys. It measures we measured the topography first of bulk intermetallic crystal, and it has unusual magnetic properties. It's useful in sensors or advanced prosthetics. And we can see that it's smaller because there was bigger area of interest measured. In the magneto-optic Kerr effect, we see the same like structure. So with Lite Scope, we were able to fastly control over area of interest, and where TEM was unable to see the native domains at the room temperature, MFM resolved this complex pattern quite easily. And so here is another example of polycrystalline cobalt. We see the lamella here. First, the chunk was fib-milled, then localized the area of interest, and then navigated using the tip. So as we have the navigation here, we have the area of interest. In backscattered electrons, we see two structures which we'd like to measure in MFM. And we see how the structure actually looks like. So it was quite surprising what we saw. And so if you'd like to know more information, you can visit our webpage, or we post regularly on our social media. And we have YouTube account with more video, more recordings if you'd like to see. You can meet us in person in some conferences. We will attend Materiae in Portugal, in Finland, in Germany, in France, and in the United States. So if you attend some of them, you can talk to us. I'd like to summarize. LiteScope is a compact and easy to use AFM in SEM. We are able to measure under in-situ conditions, multiple techniques together, and use fast and easy area of interest localization. We were talking about how to measure mechanical, electrical, and magnetic properties, and introduced several of these techniques. And so with this, I'd like to continue answering some of the questions, as I saw many of them were there. So, okay. So the first one is nanoprobe electric ready for simultaneous measurements of topography and current through the sample and through the tip. So nanoprobe electric is capable of measuring topography and the current through the sample, and measurement of current through the tip is being developed. And so does it come with a heating function? Heating and cooling is being developed, so it will be released within a year. And so the third one is, Do you observe some shift or drifting in AFM scanning, or you are usually performing the scans without the beam being on? Well, during the measurement, there are some drift. However, we developed using artificial intelligence optimization, where you can automatically solve this problem. But usually the beam is always on and we are measuring simultaneously AFM techniques and SEM. And so there were quite a lot of interesting questions, so I have a few more. AFM and SEM may be done simultaneously, but what about KPFM and SEM? Would the beam not interact with the tip potential? Well, it is possible to measure KPFM and in SEM, but we have to be careful about where we use the electron beam, because of course we can change the surface potential as we are using as we are scanning with electron beam. But sometimes it's the object of study to actually use the electron beam to change something or to see how it's lowering the surface potential as we first use the electron beam and then we turn it off and we are waiting to see what's going on. Another question is, should this combination produce the noise? If we properly install the device, so we have the same electric circuits, the noise shouldn't be the problem. So well, there was so many questions, and so with this, I'd like to thank you for your attention, and thank you for attending this webinar and a lot of questions. I would like to invite you to our next webinar in June, and we will keep you informed on the social media. If you have any questions, we still be online for some time, so you can ask in the chat and we will answer. And if you have any question in the meantime, during the webinars, you can contact us directly on application@nanovision.com. Have a great day and bye.